Okay, good morning, everyone. Welcome to the Mini-Moon Seminar number 37 of Taiwan Space Union. So today we are very happy to invite the Professor Shinichiro Sakai to give a talk. So Professor Sakai is from the Institute of Space and Astronomical Science of JAXA. So let me introduce him. He got a PhD degree in electro engineering of the University of Tokyo in 2000. After that, he just joined the ISS. So his research field included space guidance, navigation and control issue, and electromagnetic formation flying. He also participated in several scientific satellite missions such as Leme, Astronautical, Isaki, and Alase. So from 2016, he is also a project manager of JAXA's small lander SLIM for a pinpoint landing. So today, Professor Sakai will give a talk about this lander. So let's welcome him.
Okay, thank you very much. And let me first starting sharing my screen. So just a minute, please. So I will start my presentation. And thank you for coming to today's seminars. And as Ian-san kindly introduced, today's topics is about a small lunar lander named SLIM. And as you know that so many landers from many countries have already succeeded to landing on the moon. However, our lander has a unique point comparing to these conventional or recent landers. So in my talk, I will introduce about the unique point of our landers and introduce some technologies which are developed for this spacecraft. And after that, I will introduce some activities which SLIM will carry out when it succeeds to landing on the moon. So the starting point is the comparing with traditional or conventional landers with SLIMs. And as you know, many landers have already achieved ground landing, such as Apollo, or Lunar series, or Chang'e, or Chandrayaan-3, and so on. And basically, these landers targeted sea area on the moon, and sea means, of course, a wide and flat area on the moon. It means that in these cases, required landing accuracy or landing ellipse is several kilometers or 10 plus kilometers. And the traditional navigation technology based on the orbit determination on ground was enough to meet this requirement, such as the several kilometers or 10 plus kilometers. And this is a photo on the moon. And this area is a very famous area named Sea of Tranquility. This is famous. This area is famous because the Apollo 11 was landed on these areas. And as you can see, that of course, the sea of the moon is a very wide and flat area without large craters. And just how to say, next area such as here or here has a very complicated shape with mountains, rocks, or craters. And as I mentioned, that the traditional landers or even recent ones such as Chandrayaan-3 basically landed on these areas. Sorry, this table is just described in Japanese, but the point here is that you can see the number of the requirement for the landing accuracies. This is just based on some opened information. So not so many information is open for each landers. But based on our investigation, for example, that the landing accuracy requirement for Chang'e series seems to be 6 kilometers. Or if we mention about the Chandrayaan, it seems to be about 30 kilometer and 15 kilometers. Landing accuracy for the traditional or recent lunar landers is something like this. But if we think about the lunar landing mission tomorrow, the requirement seems to be changing nowadays. One reason might be the recent lunar orbiters, such as JAXA's lunar orbiter named Kaguya, which was launched in 2007, and NASA's lunar orbiter, a very famous lunar orbiter, LRO, which was launched 2009. And these spacecraft provide an enormous amount of image data with high precision, such as 15 centimeters, and very precise terrain data, or called DEM data, digital elevation map data, and some information to estimate the composition of the lunar surface. Therefore, scientists comes to focus on some specific area or target. And typical conversation with lunar scientists nowadays might be like this. So they say, I would like to investigate the rock nearby that craters. So this is just how to say, explaining about the image of such conversation. I mean that this is not the actual target area for our landers. But anyway, that some discussion is like this. So the scientist found some very fresh crater like this here or here. And then they also find some very interesting rocks, which seems to be come from the inside of the crater areas when when this crater was generated. So the scientists say that I would like to investigate this rock. So the lander should land on these areas. And this red circle indicate the 1 kilometer diameters. So if the lunar lander has the capability of landing accuracy about few kilometers, it is of course impossible to land on these areas. And the landing accuracy is required from another aspect. From the aspect of the safe landing, landing accuracy should be very, very important because, as you can see, such area has very complicated terrain. It means that if the lander has only 1 kilometer accuracy for landing, it might land on this area or these areas. And as you can see that the terrain is too complicated for safe landing. So in that case, some hazardous event should happen when the lander try to land. So both from the mission objective and the safe landing accuracy should be very, very important for tomorrow lunar missions. So we name such technology, I mean that the accurate landing technology as pinpoint landing. And we thought that this pinpoint landing technology should be required for the future lunar landers. And of course, that as I mentioned, conventional lunar landers have not achieved such pinpoint landing yet. It means that we have to develop some novel technologies to achieve pinpoint landing capabilities. So our institute, ISAS, JAXA, started SLIM project to demonstrate pinpoint landing technology with small and lightweight lunar landers. And our target accuracy is 100-meter accuracy. So you can understand this is a quite huge jump from this accuracy to this accuracy. Order is different. And the name SLIM is coming from a smart lander for investigating moon. And this project was started in JAXA from 2016, and it was defined with two main objectives. One is as I mentioned, to demonstrate pinpoint landing technology with accuracy of 100 meters. The other one is to develop elemental technologies to realize small and lightweight lunar lander to enable frequent lunar and planetary missions in the future. And this slide is showing you the visual appearance of our spacecraft. And the weight is about 200 kilogram in the dry configuration. Dry configuration means the configuration without a propellant. And the weight at the launch or the filled with the propellant is about 700 kilograms. So it means that the weight of the propellant is about 500 kilograms. So at the launch configuration, most of the spacecraft is the propellant. That is because that the spacecraft have to travel to the moon and achieve the landing. And the size of the spacecraft is about 2 meters or 3 meters. So maybe if you think about the size of the small automobile, that might be a little bit similar to the size of our spacecraft. And the launch vehicle for our spacecraft was a Japanese A2A rocket. And it was a dual launch configuration. It means that the stream is a little bit too small for a single launch. So, so-called dual launch configuration was applied for this launch. And the other spacecraft is also our institute scientific spacecraft named GLISM. That is a satellite for the X-ray observations. And this is a rough sketch about the trajectory or the way to the moon. I will show you the actual trajectory data in the latter part of this presentation. But anyway, that the rocket will separate our spacecraft in the Earth orbiting low Earth orbit first. And after that, the stream is changing its orbit using the propulsion system on the spacecraft, like this. And at this point, we had timing of the so-called the moon swing by event. And after that, the stream is traveling around a little bit far from the Earth, and finally approaching to the lunas or moon. So for a while, I would like to talk about the technology for pinpoint landing. So first of all, we should discuss about what are the difficulties to realize pinpoint landings. One point is, of course, the limitation of the on-ground orbit determinations. On-ground orbit determination is usually achieved using the telecommunication instrument, or, for example, measuring the traveling time of the radio wave, or monitoring the Doppler frequency to measure the velocities. However, on-ground orbit determination provides us only insufficient accuracy for pinpoint landing. Another problem of the on-ground orbit determination is that it is usually a non-real-time operation. It means that the on-ground determination is based on some estimation of the trajectory information. So the calculation takes many times, not real-time calculations. So it's a bit difficult to achieve pinpoint landing just based on such on-ground insufficient on-ground orbit determination technology from the viewpoint of accuracy and real-timeness. And of course, that as you know, GPS system cannot be available around the moon. It's too far from the GPS satellite. Second point is that it might be a little bit complicated, but some mismatch between the image data and position data should be also taken into account. So usually scientists point out their target landing area on the image data, like this area next to these craters. However, we have to say that each image data about the moon have some mismatch between the actual position data and indicated position data. Because image data of the moon it was captured by some orbiters like Kaguya or LRO. So the position data of the image data is depending on the orbit determination accuracy of these orbiters. And it's a bit difficult to evaluate, but some specialists say that we have to always think about some tenth meter or 100-meter mismatch between the image data and the position data. So that is also a big problem to achieve the pinpoint landing. And the third point is related to the dynamics of the landing. I have to say that the descent and landing process on the moon is very speedy and dynamic event. For example, that when you start the final descent process, the lander will land within only 20 or 30 minutes. So autonomous guidance and navigation control system is necessary to achieve pinpoint landing. It means that the lander could not rely on the on-ground support. Autonomous system is very important to achieve pinpoint landing because dynamics is too fast. So the solution in our spacecraft is something like this. First point is about the navigation or the position information accuracies. And the vision-based navigation system was developed for our spacecraft to know the very accurate and real-time position of the spacecraft. The mechanism is, roughly speaking, like this. So the SLIM spacecraft has onboard camera to capture the surface image of the moon like this. And the SLIM has already have some system for the image-based calculation. So it indicate or it find out some point as crater on this image data, like this or like this or like this. So next step is the identification of the location of this image on the huge map data, like crater map data like this. So some calculation step like the pattern matching is applied for this identification. And finally, the onboard system can find out the area which is matching to captured image from the viewpoint of crater distributions. Then a spacecraft knows its position based on these image-based identifications. First step is called crater identification, and the second step is called crater matching. And very important requirement for vision-based navigation system for pinpoint landing is the calculation time. As I mentioned, that the descent and landing process is a very dynamic one. So real-timeness is very important. It means that such vision-based navigation should be completed or have to be complicated only 1 or 2 seconds. Unfortunately, current space-grade CPUs have only about 1/100 of the calculation speed compared to those used on the ground. It's very slow compared to the usual computer on ground. So, generally speaking, it's not so easy to achieve 1 or 2 second calculation time using such slow CPUs. So ISAS and our institute and several universities such as developed novel algorithms on space-grade FPGAs, enabling accurate positioning with only 1 or 2 seconds. This is a, how to say, very important point for our development. That is why we can start our project. And now I'm showing you the final descent and landing sequence. The final descent process will start from 15-kilometer altitude. And after that, vision-based navigation performed at several points. Not always applied, but only at several points. And so each point, we have the updated information about the precise position and velocity of the stream lander. Then autonomous orbit correction was calculated based on the updated position and velocity position and velocity to accurately reaching to the target point. This autonomous correction or autonomous control is another very important aspect for the stream to pinpoint landing. And finally, it is in the process of so-called vertical descent phase to achieve pinpoint landings. And as I mentioned, that in all steps, all process is about 20 minutes or so. And this is a zoom up explanation about the final landing sequence or a vertical descent phase. And at this point, that the altitude is decreased about 5 or 6 kilometers. And at such area, we can start to use landing radar, which is also on board on the stream. And this landing radar can measure the altitude and the velocity with radio wave informations. And at about 500-meter altitude, we applied final vision-based navigation and got updated and accurate position informations. And of course, that the stream trajectory approaching to the target is collected based on this updated information. And finally, at 50-meter altitude, another vision-based system is applied to find out the obstacle, so-called obstacle detection to achieve safe landing. And about 2 meters, we deploy 2 very small rovers. And after that, stream wheel landing like this. So I will also introduce some novel technologies to achieve small and lightweight spacecraft. So this one might be a little bit interesting one. This is the so-called lightweight shock absorbers. And the point here is this is the crushable lattice aluminum structures which can absorb a landing impact. So this is a video which is showing the behavior of these materials. And at the landing, this material could be crushed like this. And during this process, it will absorb the landing impact to prevent some hazardous issue on the onboard hardwares. And for example, that in traditional landers such as the Apollo are using a leg system with the mechanical dampers to absorb landing impact. And that is a very good system, but for our spacecraft, that is too big and too heavy. So we developed such lightweight, crushable mechanism to achieve very lightweight landing impact absorbers. Or we developed also some batteries or solar cells which has the lightweight characteristics. And these are the two main engines which generate the main thrusting force to change the orbit or to achieve the pinpoint landing or the descent. And these are the bit unique thrusting system because this is not a metal thrusters, but ceramic thrusters. So basically speaking, that it can survive more high temperature compared to the metal materials. So it can achieve a more efficient thrusting system. And that is very important to realize lightweight landers or spacecraft. And another point to achieve lightweight spacecraft is the main structure of the spacecraft. As I mentioned, we have to have a huge tank to have about 500 kilograms propellant. And our tank is, at the same time, is the main structure of the spacecraft. It means that this spacecraft has not a rigid body system, and very roughly speaking, that the component is directly attached to the tank. So it means that we can reduce the weight of the body structures, and that is also, how to say, another approach to reduce the spacecraft weight. So this is another slide to showing some detailed point about lightweight shock absorbers. And in some time in the development history, we have to solve one problem about these shock absorbers. And the problem was how to manage the manufacturing quality of such lightweight absorbers. Because it is a lattice structure, so it might be a little bit difficult to find out the way to manufacture it with required qualities. And our answer for this question was manufacture with 3D printers. And we are very lucky because almost at the same time, 3D printer technology is very rapidly developed. And at some timing, we could find some system which can provide such metal-based object with 3D printers. And this answer was found out with a collaboration with a researcher in a university. So the SLIM project is, how to say, have many relationship between the researchers in the university, and they support our research and developing process so much. So, okay, so this slide is introducing you the post-landing activities. As I mentioned, main objective of SLIM project is to demonstrate the pinpoint landing on the moon. However, some additional missions are also planned after the successful landing. One is the scientific observation with so-called multiband spectral camera, and the other one is engineering experiment with two small rovers, LEV-1 and Level 2 or Syracuse. And first, I will introduce about these two small rovers. And the Level 1 is developed by our institute with university cooperation. And Level 2 is, of course, JAXA is involved, but mainly developed by some private company in Japan, like the Tomy or Sony or and some universities. And the unique point of the Level 1 is its mechanism for the locomotion. And the Level 1, this is some kind of the experiment for the lunar surface locomotion. And the how to say point here is this rover will hopping on the moon. I will show you the video in the next slide. And the unique point for the Level 2 is that this is basically developed with Japanese private company, and Tomy is a company which is providing some items for children. It means that such company is from now on, until now, this company has no relation to the space activities, but they are coming into this field and collaborate with JAXA to provide such very unique rovers like this. And as I mentioned, these two rovers will be deployed from the stream just before the landing. The approximated altitude of the deployment is about 2 meters. So this is a video of some experiments with a hopping motion of Level 1 on ground. So it seems to be a very short distance with this one hopping, but of course on the moon the gravity is comparably small to the Earth configuration. So we expect that the hopping distance on the moon should be 6 times longer compared to these demonstrations. And this rover has, of course, the capability to change the direction of the hopping like this. So the step is first rotating like this to change the direction of the hopping. And after that, they generate a hopping motion. And it could repeat these behaviors in between the hopping and changing the hopping, change the direction, hopping, change the direction. So it can achieve some distance with locomotion. And this is a video to introduce the motion of the Level 2 or named Syracuse. So first, it deployed like this on the moon. And after that, they moving a little bit unique motion like this. So it is expected to have a capability to move on the sand on the moon or regolith on the moon. And so, okay, so that one, sorry, this one was a camera on the level Q, and it means that the both level 1 and level Q or Q has a camera. So we expect maybe they can shoot some image after the stream, after the landing. So we would like to have some scenery from the outside of the stream after the landing. And another post-learning activity is a scientific observation using some instruments named multiband spectral camera or MBC. So after landing, this MBC will investigate the composition of the surrounding olivine thought to be originated from the mantle of the moon to obtain clues that could lead to to understand about mysterious about moon's formations. So the target landing point for stream was selected to taking into account these scientific activities. It means that as I mentioned, the target of the MBC is olivine derived from the mantle. So it means that we stream should land on the area which is thought to have olivines derived from the mantles. However, only some specific areas meet this condition. I forgot the specific numbers, but some only 20 or 40 points are identified to have origin derived from the mantles. And unfortunately, all of them seems to be very, very complex terrain. The reason is quite simple because such olivine is only exist very near area to some craters, and the area close to the crater is always have very complex terrain. It means that pinpoint landing capability is very, very important to achieve such scientific observations. Again, to land on the target position and achieve very safe landing. Pinpoint landing is the key technology to achieve such landing. And finally, we find out some target landing point close to named Shiori crater near Mare Nectarius. And this area is constantly sloped to approximately 15 degrees like this. Of course, we would like to find out more flat area, but we couldn't. For our investigation, this is the most, how to say, good landing point, even from the landing safety. So we decided to have a capability to land on such slopes. That is why we developed a little bit unique landing scheme that is named two-step landing. As I mentioned, that is the reason why we have to choose like this is that we have to have a capability to land on a slope to carry out the scientific investigation using multiband spectral cameras. And the landing scheme is something like this. First, the spacecraft is approaching to the surface vertically like this. And just before the landing, the spacecraft attitude is changing toward to the slope, like this. And first, this leg is touch on the surface. And after that, the front leg is touch on the surface. And finally, the spacecraft attitude is stabilized like this. And as you can see here, like this, we carried out so many numerical computer simulations and some experiments to find out some configuration to achieve such safe two-step landing on the slope like this. And we conclude that this scheme is more safe compared to the traditional landing scheme or the vertical landing scheme. Okay, then I'd like to introduce some steps for the launch of the SLIM spacecraft. So these photos are showing the final steps of the development process. And at this time, the spacecraft is already ready for the launch. So we have to apply so many system tests to validate the configured spacecraft. This is a photo for the so-called thermal vacuum test. And this is a photo for the mechanical vibration test. This test is very important to check the validity, to check the behavior of the spacecraft in the thermal condition in the space. And this test is to check the survivability of the spacecraft against to the huge vibration on the rocket. And this is very similar test to this. This is so-called acoustic test. And this is the scene from the so-called fit check with a rocket adapter, this one. And after such system test, finally, the SLIM spacecraft was transported from the factory, which was located in the Kanagawa prefectures, to the launch site in the Tanegashima Space Centers. So it was transported on land and from here to here on the ship. Again, that the transported on the land, and finally, again, loaded on some ship, transported to this Tanegashimas. Okay? And these are the photos after transported to Tanegashima areas. And this is a timing for to approach to the Tanegashima Space Centers. And again, we have to apply some test after the behavior check after the transportation, like this. And finally, SLIM and GRISM was launched on 7th of September, just about 2.5 months ago. And because, as I mentioned, this was the dual launch operation. So on the top area, the algorithm was located like this, and just under the algorithm spacecraft, our SLIM was located here. And the launch itself was very beautiful one. And it was a very difficult timing for us because this season is a typhoon season in Japan. So the launch was delayed again and again because of the typhoon issues. But fortunately, finally, our spacecraft was launched on 7th September, like this. And but I wasn't on the Tanegashima area at the launch timing because our launch room, our operation rooms is located in the Kanagawa prefectures. So this is the photo in the operation room, SLIM's operation room, just at the launch. This is the time for almost just the same as the launch time. So everybody is watching on the scene for the launch of the H2A rocket like this. And this just because this is operation room, so from this room we send some command to the stream and receive some telemetry data from the stream. And the operation is, of course, using some antennas or ground stations. And JAXA has many ground stations in Japan. So we are mainly using some large antennas located in Nagano Prefecture and the Kagoshima prefectures. The diameter of the antenna is about 34 meters and 64 meters here and here. And JAXA has also antennas outside Japan, some point in the world, we have some some antennas for the operations. And this chart is showing you some example of the combination of these antennas. Just because was very important operation day, so we combine many antennas to have some redundancies. And this antenna is in Japanese in Japan, and these are outside Japan, but JAXA's antenna. And at this time, we also use a NASA's Deep Space Network antenna as a redundant one. So we combined many antennas for important operations. And this video is showing you the journey to the moon. First, as I mentioned, SLIM is launched in the Earth orbiting orbit like this. And after that, we generate some propulsion to change the orbit. I mean that try to elongate the apogee altitude. And finally, once it meet with moon, but this is just the swing by timing. So the SLIM is not captured by Moon, but going into some another very large orbit like this. And finally, at that point, SLIM meet Luna again. Then we again generate a huge maneuver trying into the Earth, lunar orbiting orbit, like named lunar orbit insertion. And after that, about 1 month or 2 months, SLIM will orbiting around the moon and gradually changing its altitude or reduce the altitude, approaching to the moon like this. And I think that this is the orbit with 600 kilometers by 600 kilometers. And just before the landing, again, we changed reduce the altitude of the orbit again to 15 kilometers by 600 kilometers. Okay, yeah, this one. And finally, SLIM will try to land on the moon. So the schedule of the journey to the moon is like this. As I mentioned, that on September 7th was the launch date, and we start the journey to the moon from the first day of the October's. And after about few days, it very close to the moon once, but this is just a swing by event. So after that, SLIM is going around a large orbit like this. And on the 6th of this month, it passed the farthest point from the Earth. It was about 1.3 million kilometers from the Earth. And this is not today, a few days from now on, but anyway, that SLIM is located around here. And someday in the December, we have a very important event, which is named lunar orbit insertion. After that, SLIM is in the lunar orbiting orbit. And the landing operation is after the lunar insertion, SLIM will gradually decrease the altitude of the orbit. And the perigee altitude of the final orbit will be approximately 15 kilometers. And SLIM will start its final descent and landing sequence from this point. And landing date will be someday in next January or February. And once SLIM starts its final descent and landing sequence, it is impossible to stop the sequence because of the large gravity of the moon. And final sequence is estimated to take approximately 20 minutes to go to the landing. And the sequence is the autonomous one, and operators will basically only monitor the status. So at the end of the presentation, I will mention about the history of the SLIM. So as I mentioned, the development itself was almost ended about this year. And during the development, we have some milestone of the review process named critical design review or preliminary design reviews. And the starting point of the SLIM project was about 2016, about 7 years ago. But it has a little bit more longer stories like this. The origin of the SLIM project was about 2002. At that time, that some group in our institute was researching some second mission, which is successive to the Kaguya missions. But at that time, JAXA was not approved to such activities. So 2012, our project was first proposed to the ISAS or JAXAS. So as I mentioned, that it means that it has a very, very long history for the development or the research about the SLIM project. To be honest, certainly, I just involved in this project just about 2014 or like that. But the researcher who first thought about the SLIM, for him, it is about 20 years activities. And finally, last 20 minutes will decide our trial will success or not. So for us, it is a very, very important 20 minutes, I expect. Okay, so I think that I have almost spent my time for the presentation, so I will conclude my presentation. And if you are interested in a project, for example, that we have some information on the Twitter system. So if you have some interest, please check our Twitters or homepage or something like that. Okay, thank you very much.
Yeah, thank you very much for your nice talk. So, anyone has a question from our audience?
Yeah, I have a this Wing Yip, I have a question about at some point you talk about this very interesting, you call that rover, tiny
Okay.
rover, solar kill.
Yep.
Can you say something more about it? Because the purpose of it is just to roll around, roll around.
Yeah, that's right. That's right. Yeah, to be honest, that the main mission is how to say, just a technological demonstration. Of course, we expect that it might be a success to capture our image. But for my understanding, main objective of this mission is to provide some chance for the commercial company, which was not in the space field. As I mentioned, that the Tommy company is a hobby company. So for them, this is the first time to involved in the space activities. So that is also very important scope for Astronautical or Level 2.
Okay, I think that's very interesting because we are looking for possibility of having such something like this on the future lunar missions. It excites the imagination of young people. And how heavy is this solar kill?
Yeah, I forgot about it. It's about 2 or 3 kilograms. So it is a very, very small one.
Okay. And other question I have is that about the landing site. Of course, you said the camera, the multivalent camera is to look for pyroxene. But then I look at the landing site you showed, and that place, because from my understanding that you have to dig up the material from the mantle. You need to have a very deep, a large crater. And the one you showed in the picture, that seemed to be a young crater.
Right.
Yeah.
So as I mentioned, I'm not a scientist, but the scientists say that important point here is the freshness of the craters.
Okay, right. Yeah, because the new crater, fresh crater, usually they're small, and I don't know, I cannot tell the diameter of this crater. And my guess is about 5 to 10 kilometer. We could check, I could check later on. Okay. Yeah, I mean, this is very, very challenging and very interesting mission. As you said, the main point is to test the autonomous, pinpoint landing on a rather rugged, the place on the moon. And I look at the calendar, the time schedule you showed last at the very end. So because you mentioned you came to ISAS at 2001.
Right.
So this must be your first project, right?
Right, and to be honest, that at this time I was involved in another project, so I have no relation to this project. So to be honest, I was joined to Slim projects just about to 2014 or like that. So even for me, this is a very long project for about 10 years. But how to say, for the originator of the Slim, this is a 20 years project. It has a very long story.
Well, at least it is working out fine. When is the landing time? The landing date?
Landing date is someday in January or February.
Next year.
Okay. Next year, yes. So about 2 months from now on.
Let's say this. When the landing is successful, I mean, certainly it will be successful. And when after the at the end of the mission, we would like to invite you again to come here to
okay. Okay, thank you very much. So that is a very good news for me because I want to. I have never been to Taiwan, unfortunately. So that might be a very good, how to say, motivation for me to success this project.
Yeah.
Thank you very much.
Yeah, our best wishes for the success of mission, and thank you so much, Professor Sakai.
Thank you very much.
So, any question from the audience? Yes, there's one question from audience.
Okay, I understand. So the question is that why we doesn't use some commercial-based CPUs, very fast CPUs, right, or GPU? And yeah, thank you very much. That is a very nice question. And the answer is that usually space environment is very severe for such commercial-based CPU or GPUs. The one reason for that is, of course, radiation issues, and the other one is from the thermal aspect. And so, usually speaking, when you launch such commercial-based CPU or GPUs, it doesn't work in the space environment, or it will be broken soon because of the radiation issues or thermal issues. Is my answer clear for you? Okay, so
Yes,
some another student is asking about the ISAS and MHI and the okay, so. Okay, so I think that you are asking about the relationship between the ISAS and the companies who is joined to our project. Of course, that we have the contract with companies and the how to say the main company who is manufacturing Slim is not MHI, but the Mitsubishi Electrical Company, or so-called Merco in Japan. And that is the system manufacturer of the Slim project. But we also have contact with MHI because, for example, that as I mentioned, that our main engine or main thruster is a little bit unique one, which is ceramic thrusters. And that technology was developed with ISAS and MHI. So we made a contract with MHI to provide that thruster to Slim system. So we have another contract with MHI on the thrustering systems to provide that component to the Mitsubishi Electrical companies.
So, any question from audience? Or if not, I think we are out of time. So, thank you very much. Thank you very much for Professor Sakai, and thank you everyone to join us for this talk. Okay, hope your mission can success.
Okay. Thank you very much for your kind word.
Yeah,
I will try to do my best.
Okay, bye.
Bye now. Thank you very much.